Norton Theorem and Deafening Theorem are duet pair. Norton Theorem stating that a linear two-terminal circuit can be simplified by a current source in parallel a resistor. Here that's the terminal A and this is terminal B. It can be simplified or equivalency by a current source. And in parallel a resistor Rn. In is the short circuit current at the terminal, which means that this terminal is short circuited, and then we found the current. That's the short circuit current I of n. R of n, that's equivalent resistor at this terminal A and B when all the independent sources are turned off. The relationship of Norton theorem and Deafening theorem can be illustrated using source transformation. We know from the Deafening theorem, the terminal can be simplified by a voltage source in series of a resistor, so VTH and RTH. VTH is open terminal voltage, and RTH, that's the resistor when all the independent sources are turned off. And if we want to turn this voltage source in series of a resistor into a current source in parallel to the resistor, we can see that Rn is equals to RTH. What is I of n? I of n equals to VTH divided by RTH. So this is a relationship of the Norton theorem and Deafening theorem. How do we obtain the parameter for the Norton theorem? First of all, the Norton resistance is the same as the deafening resistance. Rn equals to RTH. And the short circuit current is equals to VTH divided by RTH. So if we obtain the open terminal voltage, if we know RTH already, so we can take the ratio. That's the short circuit current for the Norton theorem. Here is a summary of the relationship between the Deafening theorem and Norton theorem. The open circuit voltage, sometimes we call it VOC open circuit, across terminal A and B, that equals to VTH. So this is a VTH. The short circuit current ISC, short circuit at terminal A and B, that is I of n. Is I of n from Norton theorem. The equivalent resistance at the terminal A and B, either the notation is RTH or Rn. That's the same resistance. The resistance is obtained by turning off all the independent sources and calculate the equivalent resistance from this terminal A and B. Sometimes we call it Rn as the input resistance. This is exactly the notation here. VTH is the open circuit voltage, short circuit current, that's I of n, and RTH equals VTH divided by I of n. These are the relationship between the Deafening theorem and Norton theorem. Let's look at an example. How do we obtain a Norton equivalent circuit? This is an example. Here's current source, voltage source, and terminal A and B. So we want to find out the Norton equivalent circuit in terms of terminal A and B. First of all, we want to find the resistance, equivalent resistance. To find Rn, we need to turn off the independent sources. So this current source needs to open circuit, and this voltage source needs to be short circuited. So that's become here, and this become this. Don't worry about here and here. This is a dangling wire, didn't connect anywhere. So the equivalent resistance will be 8 ohm in series of 4, in series of 8, and then parallel 5. So that's the result is 4 ohm. Next is I of n, which is a short terminal current. So you need short this terminal, and you find the current There is two ways actually to obtain this short circuit current. One way is if we know VTH and we know RTH. And RTH we already obtained that equals to Rn. We solve open circuit voltage, we can obtain I of n, or we can find I of n directly. So let's look at this way first, because we know how to obtain the VTH from Thevenin theorem. VTH is the open terminal voltage. It's an open terminal. So terminal is open, VTH. We call it open circuit voltage. Just two notation, but they represent the same thing. This is a VTH. This is the same thing here. Here, yes, VTH. We really want to solve this circuit and obtain VTH. That's about it. In this case, we can use mesh or you can use nodal. It doesn't matter, whichever way we're comfortable with. We can use mesh. Here there are two mesh, called it I3 and I4. Currently I3 equals to 2 amp because of this current source here. That's equals to 2 amp. So one equation already obtained. The other equation is coming from this mesh I4. Let's apply KVL on mesh I4. So we walk through here. First element is minus 12 volt, and then 4 ohm. 4 ohm, the branch current is I4 minus I3 here. And then 8 branch current equals to the mesh current, that's I4. And then 5 ohm. The voltage is 5 multiplied by I4, and then come back here, that's 8 ohm, 8 ohm multiplied by I4. That's the voltage on 8 ohm, that equals 0. We organize this a little bit. I4, the coefficient 4, 8, 5, 8, so that's ended up 25, and then minus 4I3, and then minus 12, that equals 0. Plug in I3 equals to 2, and we can solve I4 equals to 0.8 amp. Then let's see what is VTH. VTH actually equals to 5 ohm multiplied by I4, because that's the voltage along this terminal A and B. That is actually the voltage along this point and this point. That's actually the voltage along the 5 ohm resistor here. And the I4 is this direction. Agree with the positive sign of the VTH. Therefore, VTH is equals a plus sign here. 5 I4 is a plus sign, no negative sign in front of 5. So VTH equals to 4 volt. Then what is I of n? I of n can obtain that equals to 4 volt divided by 4 ohm, that equals to 1. This is a Norton Theorem. We obtain the current source, the value is 1 amp, and notice the direction is flowing up into the terminal A here. The equivalent resistance is 4 ohm. Next, let's use another alternative to obtain the short circuit current, which is IN. By definition, I of n is a short terminal circuit, so we need short circuit this terminal circuit here. So I use ideal wire to connect terminal A and B. So I need to find the current flow through A and B here. And remember, there is a resistor here, 5 ohm, but because this is an ideal wire, the resistance is 0, so current will flow through here instead of here. So this 5 ohm resistance is being short-circuited. Therefore, the circuit become here. The same current source didn't change, voltage source didn't change. Basically, a portion on this side, on the left-hand side, does not change at all. This is the same thing. The only thing here, this resistor disappeared because terminal A and B is short circuit. Here there's a short circuit here. This 5 ohm resistor disappeared. It's been short-circuited. Recognize that the problem solved. Again, we can use mesh analysis to obtain this current here. So current flow in this branch here between A and B. Now again, there are two mesh 1 and mesh 2. So remember here, this is open circuit because of the resistor 5 ohm. Basically this portion, there's a wire drawn here, but it didn't do anything. Mesh I1, the current equals 2 amp. Right. Second mesh, we're going to apply the KVL. We're going to start walk here. The first element, negative 12, and then 4 ohm here. 4 ohm, the current is I2 minus I1. Okay, and then walk to 8 ohm. 8 ohm here, the current is I2, and then keep going, and then keep going. This 8 ohm, the current is I2 as well. The coefficient of the I2 is 4, 8, 8. So that's 20 I2, and I1, that's minus 4, that's minus 12, that equals 0. And then you plug in I1 equals to 2. So what is I2? The mesh current, that's equals to 1 amp. That equals to this short circuit current, and this is IN. This is the same result we obtained using the open circuit voltage divided by RTH, that exactly 1 amp. We can say there are two ways to obtain the short circuit current for Norton theorem.